Greetings and welcome to the 13th clinic of linear algebra. This clinic is going to focus on subspaces. So let V be the vector space of real polynomials. We want to determine whether each of the following sets is a subspace of V. So to be a subspace, there are four conditions that have to be satisfied, well, technically three. First is it has to be a non-empty subset of the vector space. So it has to contain the zero vector, right? The additive identity. Then it has to be closed under addition as defined in the vector space, and closed under scalar multiplication as defined in the vector space. So our first subset is a set of all polynomials with integral coefficients. Right, so what we want to do is we first want to decide, do we think this is a subspace or not? Because that's going to tell us how to proceed. If it is a subspace, we're going to prove it. If it's not a subspace, we need to provide a counterexample. Well, I don't think this is, right? So my job is to find a counterexample. So I say consider f of t equals 3t squared plus 8t minus 4. Clearly, f of t is in W1, right? All the coefficients are integers. However, take a look at 1/5 times f of t. This would be 3/5 t squared plus 8/5 t minus 4/5, right? This is not in W1, right? 3/5 is not an integer. 8/5 is not an integer. Negative 4/5 is not an integer. But 1/5 is a real number. So we say that W1 is not a subspace of V. Right, so W2 set of all polynomials of degree at least 6 and the zero polynomial. Right, so degree of at least 6. Well, we're told that the zero polynomial is in there. So the zero vector is clearly in W2. And this is clearly a subset of all the real polynomials. So I want to show it's closed under addition. So of at least 6 means we're going to deal with degree of 6 or greater. Right, so the polynomials look like this: a sub I, t sub I, right? Summed I equals 6 to infinity. Right. Using properties of summations, we can write this as a single sum Then we can factor out that ti, right? And we have a sub I plus b sub I times t to the I. But if we let a sub I plus b sub I be c sub I, then we can write it in this form, right? And that is clearly in W2. So it's closed under addition. Now if we take some scalar and multiply by a polynomial of degree at least 6, again, using properties of summations, we can write it this way. Which allows us to write this. And now we just say, okay, well, Ka sub I, we're going to call C sub I. And that is clearly a polynomial of degree at least 6. So it contains the 0 vector. It's closed under addition. It's closed under multiplication. So W2 is a subspace. W3, what was W3? The set of all polynomials with only even powers. Okay, well, that's definitely a subset, right? Now, the question is 0 in there? Well, it is, isn't it? Right, 0 would be zero times t to the 0, which would be in W3. So let's take 2. I'm going to use n this time. Polynomials of even degree only, so summation n equals 0 to infinity. A sub n t to the 2n, right? That's what it means to be even. And then b sub n t to the 2n. And this equals this, right? And now using a similar argument as before, we find that it's going to be in W3, right? So it is closed. And actually what I wanted to do was call these A sub 2n and B sub 2n. It's not going to change any of the analysis, though. We now take some scalar and multiply it by this vector. Right, we can again use a very similar argument as before. To see that it is also closed under multiplication. So we have W3 is also a subspace. I want to prove that the intersection of two subspaces of a vector space V is also a subspace of V. So let's call these two subspaces W1, W2. This would mean that W1 is a subset of V, right? And W2 is a subset of V, which implies that their intersection has to be a subset of V, right? Because remember, the intersection is all of the common elements. So if every element in W1 is in V and every element in W2 is in V, then all their common elements have to also be in V. Also, the zero vector would be in W1, right? Because it's a subspace. And the zero vector would also be in W2, right? Because again, it's a subspace. So it's in both, which means it is in their intersection. So that proves that it's a subset and non-empty. So now we have to show it's closed under both addition and multiplication. So we say, okay, let x and y be two vectors in the intersection, W1 and W2. This means that x and y are in W1 and xy are in W2, right? That's what it means to be in the intersection. But then that would mean that x plus y is in W1, right? Because W1 is a subspace. And x plus y is in W2, right? Again, because W2 is a subspace. So they're closed. But this would mean that x plus y is in the intersection, which is what we wanted. Now we let k be any real number and x be any element in W1 intersected with W2, right? Then this means that x is in W1 and x is in W2, which means that k times x is in W1, right? Because it's subspace, and k times x is in W2 because it's a subspace. But then this means, by definition, that k times x is in their intersection, which is what we wanted. So we have it's a non-empty subset, so it contains the zero vector. It's closed under addition. It's closed under multiplication. So it's a subspace of V. So we again want to determine which of these are subspaces. This time, though, the vector spaces are 3. So W1 is the set of all vectors A, B, C such that A is 3 times B. So how we can rewrite W1, right? Is this way. So we have to decide if this is a subspace. Okay. So does it contain the 0 vector? It does, right? So note, we can write 0, 0, 0 as 3 times 0, 0, 0, right? Which means it's in W1. Okay, that's perfect. So we're going to say, okay, here are 2 vectors in W1. Is there some in W1? I don't know why I wrote 0. Well, what do we get by definition? We get 3b plus 3b prime, then b plus b prime, right? And then c plus c prime. But we can factor out a 3, right? From the first component. And now that matches the form for W1. Right, so that's in W1. Now, if we let k be a real number, and we multiply it by a vector in W1, this is what we get, right? That is clearly in W1. And so W1 is a subspace. So for part B, W2, right, it's the set of all vectors A, B, C such that A is less than or equal to B, which is less than or equal to C. Well, let's consider the vector 1, 2, 3, which satisfies the condition for W2, right? So it's in W2. What happens if we multiply that by -1? Get -1, -2, -3, right? But that can't be in W2, right? Because here we have C is the smallest. But to be in W2, C has to be the largest. So it's not closed under multiplication. And so therefore W2 is not a subspace. Part C, we wanted W3 is the set of vectors A, B, C such that A times B is 0. Okay, well, consider these two vectors, which are clearly in W3. What happens if we take their sum? We get the vector 1, 1, 0, don't we? But this can't be in W3 because 1 times 1 does not equal 0. So this one is not closed under addition, right? So W3 is not a subspace. And finally, D, right? Set of all ABC such that A plus B plus C is equal to 0. Okay. Well, zero plus 0 plus 0 equals 0, right? So this means that the 0 vector is in W4. So let's do this. Let's say ABC and A prime, B prime, C prime are in W4. Notice what this means, right? This means that A plus B plus C is 0 and A prime plus B prime plus C prime is 0. Take a look at A, B, C plus A prime, B prime, C prime. Right? That would be this. Now we just have to determine if the sum of those three components is 0. Right? Well, addition is commutative and associative, so can't we group it this way? Right? Now we already know that this sum here is 0. And we already know that this sum here is 0. Their sum equals 0. Right? So then this vector is in W4. Right, now let K be some real number. So K times ABC, K times A, K times B, K times C. Right, now we want to look at their sum. Right, where we can factor out the K. And we get K times 0, which is 0. So that means this vector is in W4. So it's closed under multiplication. So W4 is a subspace, contains the 0 vector, it is closed under addition, and it is closed under multiplication. All right, so suppose that U and W are subspaces of a vector space V such that the union of U and W is also a subspace of V. We need to show that either U is a subset of W or W is a subset of U. Oops. So what we're going to do is first suppose that U is not a subset of W and W is not a subset of U. But wait, that's assuming the opposite of what we want to prove. Exactly. What we're going to do is show that this assumption leads to a contradiction. Right? Since the assumption that the conclusion is incorrect leads to a contradiction, it must mean that our assumption that the conclusion is incorrect, meaning the conclusion is correct. So what this means is there has to exist some element U in U that is not in W, and there has to exist some W in W that is not in U. Since we know that U is in U and W is in W, we know that U and W are both in the union of U and W, which means that U plus W would have to be in their union, right? Because we're told that this is a subspace. This means that U plus W is in U, or U plus W is in W. If U plus W is in U, then what we get is U plus W plus negative U, which equals W has to be in U, right? Since U is a subspace. Right. Remember, U is a subspace, and we assumed that U is in W, or is in U. That means that its additive inverse exists. However, we said that W cannot be in U, which is a contradiction. Okay. So that would mean that U plus W is in W then, right? So U plus W plus negative W would have to be in W, right? Since W is a subspace. However, we said that U cannot be in W, which is a contradiction. So we've reached a contradiction. Therefore, we have U is a subset of W, or W is a subset of U, which is what we wanted to prove. Right, and that brings today's clinic to a close. Next clinic, we'll be looking at spanning vectors and linear dependence versus linear independence. Right. Thank you all so much for attending. Thank you for watching. I will see you all in the next clinic.